Guys, today we're going to be talking about the kidneys, the renal system, or the excretory system as it's called in your PowerPoint slides in the Exam 3 folder. So Exam 3 is going to be on the respiratory system and on the excretory system. So we've already done the respiratory system, so here we go into the kidneys. It's a good idea to read through the slides first. There's going to be a couple slides that I think you may not understand. At first, just kind of gloss over those, but get the basics down so that you know what I'm talking about when I go through the anatomy of the kidney and the nephron in particular. That's what we're going to be really focusing on, are the nephrons. So if you haven't read the slides, pause the video, go back, read the slides, make sure that you're up to par on that you understand what we're talking about when we go through, so that all this will make a lot more sense. So we're going to dive right into the nephron, which, as you now know, is the functional unit of the kidney, and it consists of the renal corpuscle, which I've drawn here, which we're going to go over in a second, and then the renal tubule, which we'll go over in a couple of minutes. But for the renal corpuscle, what we want to think of first is the creation of filtrate, which is what that is doing. Filtrate is just what's happened when we have water, ions, other substances moving from the blood into the renal tubule eventually, that will, after being worked on in a bunch of different ways, which we're going to spend a lot of time on, will become urine. So we're filtering the blood here in the renal corpuscle, making the filtrate that's going to be fine-tuned as it passes through the renal tubule and eventually will be urinated away. So let's look at the beginning, the corpuscle here. Going into the corpuscle is an arteriole, and it's relatively large compared to the other arteriole anyway. And this is the afferent arteriole, and I'm pronouncing it funny. It's really afferent arteriole, but just to emphasize the A there. If you remember back to A&P1 and the afferent nervous system and the efferent nervous system, you know that afferent means going in to something. So the afferent arteriole is going in. And what it's going into is this ball of capillaries called the glomerulus. And this is where all the filtration is going to be happening. So more on the glomerulus in a minute. Now, going out of the glomerulus is the efferent arteriole, really the efferent arteriole. And we know that efferent or efferent means going away from. So it's pulling blood away from the glomerulus. Now the afferent arteriole is much larger than the efferent arteriole normally. So what happens there is that you have this kind of big vessel going into this ball of capillaries, into the glomerulus, and a small vessel is the outlet. So it helps to increase pressure inside the glomerulus. So a lot going in, not so much going out. Think of, feeling like a water balloon. Maybe the water balloon has a little hole in it. So as you put more and more water in, the water balloon will swell and the pressure will increase, and you can't get it all out through this little tiny vessel. So we can manipulate this, of course, which we will. As you read the slides, you'll know that, if you constrict this, then you have less blood going into here. If you dilate this, then more blood would be coming out. So we could manipulate the pressure somewhat, but in a normal circumstance, we want this one to be bigger and this one to be smaller so that we can have a lot of filtration, so that we can filter the blood and make a good amount of filtrate that we can then urinate away. So in the glomerulus, it's just a ball of capillaries, and these are fenestrated capillaries, which means they have little holes in them. And normally that would mean that small proteins could get out. But we don't want to urinate away our small proteins. That's not a good idea. So we have cells that cover those fenestrations, and they're called podocytes. And they form what are called filtration slits. And those filtration slits keep larger molecules like proteins and lipids in the blood away from the filtrate so that we don't urinate those away. If these filtration slits are damaged, if you look at the slide about nephropathy, which literally means just pathology of a nephron, if you damage those podocytes, damage those filtration slits, and they get big, so what we would call a leaky glomerulus, then they wouldn't be so good at keeping the proteins and the lipids inside the capillary, and you would get some leakage of proteins and lipids into the filtrate and then into the urine, which is obviously not ideal. So that would be the condition of albuminuria, where you have albumins in the filtrate, or lipiduria, where you have lipids in the filtrate. Neither one is good. Okay, so let's go back to normal function. So we've made our filtrate. We've filtered out water, ions like sodium, potassium, chlorine, bicarbonate. These are the ions that we're going to be super focusing on as we go through the renal system. All of those things will be in there. Some small nutrients like glucose, that will be in there as well. So we can determine how much filtrate we're going to create by doing this equation. So let's look at this one, this top one first. That's the simpler version. And this should look familiar to you from regular capillary filtration pressure. It is the same equation, just now we're using slightly different terminology with this G here. That G, instead of standing for capillary filtration pressure, or where we would have a N, which would be net filtration pressure, this would be glomerular filtration pressure. So everybody see the G, we're talking about the glomerulus. Then you'll also notice, instead of having an I for interstitial fluid, because we're not dealing with interstitial fluid, we're dealing with a capsule, or the capsular fluid. So the filtrate that's already been made, that's been caught in this Bowman's capsule here. So that's what that CS is standing for. So if we just substitute those different terminologies into the equation, we get our glomerular filtration pressure is equal to the glomerular hydrostatic pressure minus the capsular hydrostatic pressure. That would be the net hydrostatic pressure, which we remember from the blood unit that we did. Then we subtract from that the net colloid osmotic pressure, which is here. So blood colloid osmotic pressure minus capsular colloid osmotic pressure, so in the place of interstitial. And this should be 0, right? Because we're not supposed to have proteins in the filtrate. If this was higher than 0, that means that we had a leaky glomerulus and we have proteins in the filtrate. So that wouldn't be good if that's higher than 0. Now this, when we looked at it before when we were talking about interstitial fluid, it was kind of low, like 0, 1, 2 millimeters of mercury, not very much. It's going to be more here because we are trapping this filtrate, this newly formed filtrate, in this kind of tight enclosure, this Bowman's capsule, as we allow it to go through the renal tubule. It's going to have some pressure to it. So it's going to be higher than what we normally see, so around 15. Now the glomerular hydrostatic pressure, that's the pressure of the blood inside the glomerulus. In a normal capillary, we had it about 35 to 17 or so, depending on how dilated the precapillary sphincters were, but low, pretty low. In the glomerulus, because of the big efferent arteriole and the small efferent arteriole, it's going to be pretty high. So we have a glomerular hydrostatic pressure of about 50. So we're going to have a higher, in general, net hydrostatic pressure. Now, as for the blood colloid osmotic pressure, that stays the same. That's just typical of you. So whatever your blood colloid osmotic pressure is, that's what that number will be. So a normal number would be about 25 millimeters of mercury. So if we do the math here, it comes out to 10 millimeters of mercury, just as a nice little average example number. And that is a nice, strong filtration. If you got this down to, say, 0, so maybe you lowered this to 40. So if you put a 40 here and ran the numbers through, then you would come out with a 0 filtration number, which means no filtration is happening. And remember, the purpose of the kidneys is to do filtration. So that would be terrible. You don't want to have that happen. Now, ways that that could happen would be if you constricted the afferent arteriole, so to such a degree that no blood was going in. This does happen occasionally when your sympathetic nervous system is really, really activated. So as long as it doesn't last for a long time, that's not so bad. You just don't want it to be a consistent sort of situation, which could happen if your blood pressure was really, really low, profuse bleeding, things like that could cause that to happen. Now, we could also reduce the glomerular filtration pressure by increasing that number. Decreasing that number. Sorry, getting all mixed up. So if we decrease that number, so if we had a very, very low protein number, that would actually increase. I'm sorry, my math skills are terrible. That would actually increase our number right there. Right? Okay, so if we're good with that, we're going to move on and we're going to add the two little fun qualifiers in front of the net hydrostatic pressure and in front of the net kaleidosmotic pressure. And these should look familiar to you too. They're the same as they were before from the blood unit. So KF and this little squiggly thing here, where the KF is the filtration coefficient and the little squiggly thing is the reflection coefficient. So let's talk about the filtration coefficient first, then we'll do the reflection coefficient. So for the filtration coefficient, it's modifying the net hydrostatic pressure. So if you increase this entire thing here, you're going to increase your filtration pressure. Now, what this filtration coefficient has to do with is just generally how permeable any given capillary is. And when we apply it to the glomerulus, we think of it being super permeable because it's fenestrated. It's also a big ball of capillaries, well, a little ball, but in terms of capillaries, it's rather large. And that gives it a big surface area. So it's going to have a nice, strong filtration coefficient, which helps to increase this whole term here, which increases this. So the bigger this number gets, the bigger that number will get. Now for the reflection coefficient, this is altering the entire net kaleidosmotic pressure. So if we think of this being a larger number here, that's going to decrease the glomerular filtration pressure because you're subtracting a larger number. If this was a smaller number, like say 0, it would make this whole thing 0, which would then tend to increase this, okay, since you're subtracting a smaller number from the total. So the reflection coefficient, if we think back to what we know about reflection coefficients, it has to do with whether the capillary is a sinusoid capillary or a fenestrated capillary or a continuous capillary. And typically, if we had a sinusoid capillary, say, it would be 0. The fenestrated capillary would be a also rather low number, and a continuous capillary would be a higher number. And then when we're talking about reflection coefficient, a high number is 1 because it ranges from 0 to 1. So the reason why it's that way, so a very low number for a capillary that has really big holes, like a sinusoid capillary, where proteins are getting out, those proteins are contributing to this number, which is making this whole term smaller. The higher this number is, the bigger number you're subtracting from your B cup, the lower this is going to be in general. So like, let's say we had a B cup of 25, which is normal, and then we had a capsular kaleidosmotic pressure of, say, 0. Let's just do that. This whole thing would be 25. If we increased this to, say, 10, then this whole thing would be 25 minus 10 is 15. So that's what this is dealing with. Now, because we don't typically in a glomerulus have a number for this, this should be 0, because of those podocytes causing those filtration slits. This number shouldn't be as low as what it would normally be for a fenestrated capillary. It should be much higher than, well, not much higher because it can't go any higher than 1, but it will be very close to 1. It won't be 1 because it is not as impermeable as a continuous capillary, but it is not nearly as permeable as a fenestrated capillary and ought not be permeable at all to proteins. So in a nutshell, the glomerulus, I know I've talked a lot about these, the glomerulus is going to tend to have a high filtration coefficient, which increases your glomerular filtration pressure. It'll also tend to have a relatively high-ish reflection coefficient, which is going to tend to decrease the glomerular filtration pressure. Now, it's not going to be enough to make it too low in a typical situation, so that's okay. We don't need it to just be as high as we possibly can get it. We just need it to be high enough to have filtration. So any number over 0 is good. 10 is a nice strong number. Okay, so that is it for the hydrostatic forces and the pressures and filtration pressures of the nephron. And we'll break here and we'll come back for some more about the renal tubule.